All right, guys. Oh, actually, I better turn this thing on, shouldn't I? Yeah. All right, guys. We'll make a start. What I might try and do is upload the assignment for you next couple of days, next 2 or 3 days, so you can look over and see what it's all about and know what work's to come. It does come with a podcast, so I've sat at home and, recording away with the recording software, making mistakes, but you can sort of dub over it. So it won't be one of those sort of funky YouTube ones where I'm sort of moving around. It's just a podcast, so it just talks through different forms of validity and reliability, so you don't have to go and look them up. You can just listen to the podcast and then know a little bit about how to do the assignment. So it's all. Only trouble is it's 45 megs, so I'll have to come to the university and download it from last year, upload it. So it's not one I can just sort of email to myself and upload. All right, well, today's session, I'm going to have a look at regression. So we're going back to look at metric level data. So we'll start off with a bit of a review of linear regression, which sort of is pretty similar to multiple regression, which of course has more than one predictor variable. And then we'll talk about the different types of regression. So the difference, for example, between hierarchical versus stepwise and statistical regression. And have you covered some of those things before in third year? Yeah? Pardon? A little bit. Yeah. Might have talked about it, yeah. Well, unless you're thinking about schedules of reinforcement or something, that might be me, might be Rena. But anyway, I'll talk about different types of regression and different sort of logic underlying each of those. And particularly look at the difference between moderation and mediation effects, which are quite important and often confused. You can actually do a thesis or a study where you look at both moderation and mediation in the same study using the same variable. So it's a bit weird. You can sort of do stress as a moderator, stress as a mediator in the same study. And I'll explain the difference between those two. I won't cover path analysis. I think it was 1 year, 2015, where I covered it, but it's a bit too much to squeeze in. But there might be a few of you who might be interested at some point in doing that type of analysis. I can give you I've got like a sort of a Paul's guide to path analysis, which I can give you, and then that's a guide to simple path analysis. Of course, the more hardcore version of that is using Lizrel and Amos and some of those other packages where you're using structural equation modelling, that sort of stuff. That's the classic form of path analysis. Only for the brave, but it can be useful occasionally. Actually, it's most useful for things like confirmatory factor analysis. So if you're doing any work with Nick Burns on validating intelligence models and that sort of stuff, you might come across those packages in relation to confirmatory factor analysis. Okay, simple linear regression. Now, the basic principle of simple linear regression is to develop a line of best fit. And this goes back to, bring back memories probably of other studies and school and various things where you study this stuff. So basically you've got a variable x, a variable y, and you've got a whole swarm of points all over the place, and you want to develop the line which best cuts through the middle of those points, which minimises really the distance between those points and the line. And the way in which it does that, of course, is it works out the best sort of pivot point or y-intercept, and then it works out the best slope, the sort of angle which the line should go through the points so as to capture that function mathematically in the most accurate way. So that's a line of best fit. And of course the basic function looks like this. It's y equals mx plus c. You'll be familiar with the old linear equation. It's scary to think my son will be getting this in 3 years, in year 10 or year 9. So you've got the y-intercept, and then m is a slope parameter. It's the angle which the line goes. And that's the basic linear equation. Of course, with multiple regression, it goes into more calculus-based solutions where you've got multiple predictors. So those of you who are familiar with the mathematics of that, sort of part differentiation and various other methods are used to capture the parameters for multiple regression, the actual separate predictors. But the way in which to understand regression is just to use a simple example. It's slightly an evil example, but it's one you'll remember because it's basically, imagine, I actually had to do this analysis a few years ago because Ted Nettelbeck once, who used to work, he asked me once, is there a correlation between third year and honours marks? So are your honours grades valid? So are the guys who are getting the top marks in honours the guys who got the top marks in third year? And how many people who didn't do that well, just scrape into honours, get really high, get first, and blah, blah, all that sort of stuff. And it was actually pretty good correlation, actually. But third year isn't destiny, because there are some people who do great thesis and jump up, and occasionally a person who's a really high achiever who has a thesis doesn't work out, maybe one or two, one a year maybe occasionally, but some years none. But essentially the idea works like this. Imagine you've got a friend who did honours last year, and you ask me, well, what did, you ask Caroline, whoever it was, what did my friend get for honours? And if I didn't know anything more than that, I could say, well, I don't have access to your friend's mark, but the best I can do is say they were quite a bright class, so the average is about 82 or 81. So the roughest, dirtiest estimate you can ever give someone is just the average of the class, the average. We call this like Y bar. If, on the other hand, from previous research, we know there's a relationship between third year marks and honours, like there's an equation expressing that relationship, I might ask you, well, what did your friend get in third year? And you might say, oh, she got this, this, and this, and this. Okay, so her third year average was about, 78 or something like that. Okay, we've got an equation which predicts your honours mark based upon your third year scores. So let's say your friend's actual mark was here, and this is the roughest class average estimate you can give. You're a long way off what the actual mark is. That's like a great big error. So that's a total variance. That's how far you're off the actual score, the Y score from the Y bar. But then, when we introduce your snazzy equation, and you slot in your X value into the equation, you now predict Y hat that her score is there. And so you've got closer to the actual score. And once you sort of understand that concept of the actual score, the roughest estimate, and the predicted score from the equation, you basically can break these little lines into components. This bit here, Y take Y bar, is the total variance. Y take Y bar is the total variance in the model. It's the difference between the actual score and your roughest estimate. Well, you've got no, basically, you haven't got any real equation, you haven't got anything to predict. And of course, you can do that for every single person and get a total sum of squares. Different people use different acronyms or abbreviations. So you come up with a total sum of squares. So for every ith person in the sample up to n, this is the total sum of squares. Some diagrams people talk about this as the total variance of y, and so the total variance of y is often given like a big circle, like a great big pizza. And at the moment you've taken no bites out of it, you haven't explained any variance. But now we can start partitioning the variance into components. This bit here, which you've improved upon, this bit here for this person, that's explained variance. That's the bit you've now improved. We often refer to this as the regression component. This is the bit which you've actually explained. And so you can imagine if you did that for every single person in honours for that year for the third year mark, and then you square the difference between the predicted and the roughest estimate, this is our improvement or explained variance. This is called the regression sum of squares. When I studied economics, we always used the term regression sum of squares. It's a bit confusing. Some lecturers will probably talk about the residual sum of squares, which is actually the error one. So that bit there is the amount you've explained. It's the predicted value, take the roughest estimate, add all those up, square the difference and add them all up. That's your regression sum of squares. But of course, we're not quite there yet. Your predicted score is still not quite accurate. It's still a bit off the actual score. So that bit there, which you haven't been able to quite get, it could be down here as well. You might predict a score that's, down here. In fact, you might predict a score which is too high sometimes. But anyway, this bit here, which you haven't explained, is referred to as a residual. It's the error in the model. And so if we take y hat, the predicted score, for every single person and add them up and square them and add them up, then that's what's called the error sum of squares. So it's basically the amount of variance we've not been able to explain. So it's a bit like when you do an equation. You put your variables in, bang, and you've explained all this bit here. That bit there is your regression sum of squares. That's the bit you've been able to explain. And this is the unexplained or error variance that sits here, the unexplained variance. Of course, the bigger this is, the happier you are in your study because your model's explaining. So the bigger the chomp out of the pizza, the more you've explained. And once you understand that concept, a notion, this is what's called partitioning of variance into its systematic or explained component and its error or unexplained component. And once you've got those constructs, that's the basis for all of regression. So essentially, if you then you've got total sum of squares, this bit here, and you divide into that the regression sum of squares explained, that's what R squared is. The multiple coefficient of determination is basically the proportion of total variance which is explained by the model. When that's really high, that means your line is really close to the actual points. It's capturing, and it's white. There's a big gap from the rough estimate, the mean. So you've done really well in explaining most of the lot of the variance. So the regression sum of squares over total sum of squares is what the R squared is, and that's called the multiple coefficient of determination. And then you might ask, well, is a given value of R squared worth significant or meaningful? So say you've explained 20% of the variance, is that meaningful? Well, there's an F-test. And of course, an F-test is based on the principle, it's a ratio of systematic explained variance to error variance. All F ratios are basically ratios of systematic variance to error variance. So in basic one-way ANOVA, of course, you've got the between sum of squares, between the groups, over the within sum of squares. Hopefully your between's bigger. That means you've got differences between your groups, which are bigger than the differences in the groups. That's what makes it significant. So the F ratio is essentially draws upon the ratio of the regression sum of squares to the error sum of squares, the unsystematic variance. It doesn't use those bits exactly, but what it does is it divides these by relevant degrees of freedom to calculate mean square values. Now I've got that in the handout. I'll sort of show you what it looks like. So basically what we do is to get an F value, we just take the regression sum of squares and divide by the degrees of freedom which apply to that component. And that's simply equal to the number of coefficients estimated, take 1. So if your regression equation has 3 predictors, take 1, so 2 degrees of freedom, you're dividing your RSS by 2 to get your top bit of the F ratio, which is your regression mean square. For the error mean square, you take the total observations, which is total sample size, take the number of coefficients, which might be 3 again, take 1, and that gets you the degrees of freedom for the error sum of squares. You divide ESS by that, you've got your error mean square, and of course you divide the regression mean square by the error mean square, you've got your F ratio. So when you're looking at the outputs, you don't have to memorise all this, but when you're looking at the outputs on SPSS or R or Stata we were using, and you see an F value, that tells you, and that's significant, that means your model is significant, that means you've explained a meaningful amount of variance in Y. And what would usually be the case is your R square will be a reasonable size. So if your R square were, 40%, 0.4, it's heaps big, then it's very likely your F ratio will be significant as well. But this is the case when you've got a very big sample size, you can get a very small, piddly R squared value, like explaining 5%, but you still get a significant F value. That's, so you have to sort of interpret not just statistical significance, but also how meaningful the amount you've explained is. That sort of makes sense. That's sort of how regression works. All right, well, next thing you need to know about regression is how to interpret the equations. Now, what the output generates is an equation like this, and it uses, a bit like what we saw in logistic last week, it produces the y equals mx plus c, and these are what are called the raw regression coefficients. So it might be, for example, y equals 45.67 plus 0.67 times age. What that means is that, I always have an exam question on this, I have revision guide questions on this. Each unit increase in age is associated with a 0.67 increase in y. So I'll say it again. So what this means is that whenever you write out your actual regression equation you're going to use for predicting something, you use the raw coefficients. And then you slot in your relevant values into that equation. And what that coefficient means, the 0.67, is that each unit increase in age, like years, might be years, is associated with a 0.67 unit increase in y. If we change that, for example, to make it say, 2 times gender, it might be going from male to female is associated with a 2 unit increase in gender. In y. It's not a good example. Let's try another one. Or 2.5 times stress, or something like that. Would mean each unit increase in your stress scale means you've got 2.5 more units on y.
Why it's not like 45.67 plus 25?
Pardon?
Why it's not 45.67 plus 25?
Well, 45 is a constant. Yeah, so that just sits there. So y is equal to 45.67, that's there, yep, you put that in, plus 2.5 times the value of stress.
Yeah.
Yep, and so if stress goes up by 1 unit, then the value of y goes up by 2.5 units. 45 is a constant, it just stays there, it's just there. So if the value of stress for 1, it'll be plus 2.5. If the value of stress for 2, it'll be plus 5. If 3, plus 7.5, yep? Yes, a bit wider, bigger. You see that one now? Yep. There we are. There we go. So increase that one to, so that one times that equals 2.5. Increase it by 1 becomes 5. So, yeah. Okay. So, now, this is different. There are also what are called beta values. The problem with using these raw regression coefficients are very good for just expressing your equation. In fact, they are your equation you use in practice. But they don't tell you which variable is the most important. They're not an effect size, because the size of those coefficients will differ depending upon the units of measurement of your particular predictor. So if one variable is gender, it's measured 1, 2. If it's age and years, it's measured in years. Another one might be measured in some other units like income, so it might have a huge, great coefficient. Comparing coefficients tells you nothing about the importance of the variable. So what you have to do is you standardise those coefficients. What you do is you get the standard deviation of your dependent measure, what you're predicting, and divide it by the standard deviation of your particular predictor and multiply that by each coefficient. And that then turns it into what's called standardised beta. And those standardised betas can be compared. The bigger they are, the stronger the variable. Yeah, question? Yep. Yep.
Sorry. What do we mean by them, by multiplying them? What's them?
Oh, the actual regression coefficient. So these values here. So I might sort of write it out. So if you so a typical regression equation will have the first column. You read any sort of journal article, will have your variable, and you'll have you might have age, stress. It might have what else? Social, self-esteem. I don't know. The first column in the output is going to be, it's often called B or beta, or it's usually going to be B quite often. So this is the raw regression coefficient, and this might be something that looks a bit, and it'll have a constant down here as well. See that above the. So it might be 4.56, and then you've got minus. You have these raw coefficients like that. So when I'm talking about multiplying sy and sx, I'm talking about multiplying it by these. So age, so you can see here they're all different. You can't tell which of these is the most important one. But what you then do is you find out the standard deviation for each of these, and then the computer does it all for you. and a standard deviation of your dependent measure you're predicting. So you multiply this one here by, it'll be the SY over SX, isn't it? I think I said. Check I'm consistent when I said it, yeah. The name of it, so over age. So standard deviation for age. When you multiply that out, it'll come to a figure which is standardised. So it might be minus 0.35 or something like that. So each of these will be standardised into units which roughly run between 0 and 1 or 0 and minus 1, a bit like a correlation coefficient, although they can go bigger than 1. It's possible. And so by comparing these to standardised betas, you work out which is the most significant predictor. So what in the exam question I ask, I'll give you an output like this, and I'll say, right, write out the regression equation. And so you do it, that's the bit you'd use, the regression equation. And then I'll say, and you'll have a series of standardised betas, I'll say, which of these is the most significant, important predictor? And then you'll then look down the betas. Of course, there'll be a t-test associated with these as well. So what you do is you, having looked at your R squared and your F to see whether the model's significant, if you've explained log variance, you look down here and look to see the t values to see which of your predictors is significant, and then you use the standardised betas to work out which one is most important. So this one here, say, we're 0.5. This one will say 0.4. Oh, not constant, doesn't have anything. You'd say, yep, stress is the most important predictor. And it might be all three are significant, but that's the biggest one. It's standard in standard units. That's how you do it. So that's the difference between raw regression coefficients and standardised betas. So you use the standardised betas as a sort of effect size, work out which variable is most important, but for your equation, you use the raw coefficients. That's all makes sense? Yeah. Multiple regression, of course, is the extension of linear regression, as I said before, to include two or more predictors. Okay, so we'll go back to the, so what I've just covered, of course, is the variance partitioning of residuals. Residuals, of course, being the bit you haven't explained. That's the actual score. Take the predicted score. Talked about what R squared was, how to interpret the equations, and we just talked about the difference between those two types of coefficient, the raw versus the standard. So tomorrow when you run regression, we'll go over this all again individually. You'll run these, you'll see it on the output. I'll be coming around, you won't leave not knowing which one's which, and of course we'll have the outputs explain which ones are which, so you'll get to see how this all works again in practice. Okay, forms of MRA. Now, multiple regression, or any form of regression, has two basic forms of regression in theory. There's what's called a sort of fishing trip version of it, and then there's what's called an explanatory version of it. Regression can be used to predict where you don't really care about if it's very meaningful. So a lot of machine learning algorithms, a lot of algorithms used out there to predict various things don't really care about theory. They're simply just machines which try and work out what you're likely to buy, what sort of person you're likely to be based upon other things you do. And so it has machines running it. For example, it might be what sort of music are you likely to buy, what sort of books are you likely to buy, and it's got all this other information about you. It's harvested from Google, Facebook, various other places, or because you haven't got blockers on, it's just sucking information out of you all the time. University, I mean, my son's installed all these blockers on my computer at work, and you go into the university, just rows of trackers pop up. At my uni, you see them. Google Analytics just all down the track, harvesting information about what you're doing, so as to then work out, patterns of behaviour. To work out, if you're logging in from a certain country, they'll be tracking where you're from. They might be saying, students from Pakistan tend to look at this course and they tend to go here next on the website and do that. Therefore, this is the pathway they're coming to the website. Therefore, we need to design the front end a certain way to channel them into this place. This is how it's all being done. No one really cares about any sort of theory behind that. For example, you try and sell more things in the supermarket, more things online. There's no theory. You just chuck in whatever variables make sense. It's a bit like Freakonomics, if you've read that book. Unusual things can be related to other unusual things. And so, for example, you might find weird things like the more of a certain, people who wear a certain colour are more likely to do something else for no particular reason. Or it might be that people who read this particular type of books tend to like this type of music. And it might be you can create variables which are this book times this music times this age times this gender, all sorts of meaningless combinations of interactions to try and predict the outcome. So that's what's called prediction. And so when you're doing very practical applications for things, sometimes that's all you want to do. So I've done work, for example, I said trying to profile who might be at risk of being a problem gambler. We sort of feed in different parameters into the algorithm to try and work out which people run into trouble. The same thing happens on the online and casino-based algorithms. I know the guy in Canada who does the ones for the big casinos in Australia, and the variables are all meaningless. They're things like this guy increases his person who starts at this amount times this level of spend times this, who drops his expenditure here or adds a bet here, has a limit like this, and they use that to predict which people ultimately go on to exclude themselves or run into trouble. So that's prediction. Explanation is where you've done some correlation analysis, or you've got some sort of theory, and you've found that two of your variables both relate to the dependent measure in the correlations. You want to find out which one's the best predictor, which one's the most important thing. So if you think a lot of developmental studies, for example, with children and outcomes often based upon so-called ecological models, where you say, right, the outcomes for a child, age 10, are probably going to be, if you think of the Bronfenbrenner model, are probably going to be influenced by broader community-level stuff, like, for example, the standard of their community, whether there's parks to play in, how good the schools are, all that sort of stuff. Then we've got family-level variables, which might be, are parents working, employed, quality of housing, a whole lot of things like that. And then at the individual level, you've got the child's, it might be their intelligence, their personality, temperament, a whole range of variables that they've measured in some of these studies. And what you might do is say, which of those three levels of influence are most important? And so, like LSAC, the longitudinal study of children, enables you to do this. You could then say, right, my first block of variables in my regression are all about the background of the community. Another one's all about the family. Another one's about the kids, the individual level stuff. And that's basically a form of explanation. You're trying to find out how much variance you can attribute to each of those different influences. Same sort of stuff's done with intelligence research. Work out whether it's SES versus genes versus something else that influences scores on IQ tests too. And that's where you're actually using the regression to explain what you've got insights into at the univariate level, like just doing the correlations. It's like we're running a race. Which of my variables is going to be most important when I test them against one another? The trouble with that quite often, of course, is you get the problem of multilinearity. Do you know what you're familiar with multilinearity? Yeah. One of the major problems with regression is this issue of multilinearity. I'll write that. It will be a problem in the thesis, and there's always a problem in everything I do. So multilinearity essentially means that many of your variables, it's hard to write on the board, it's an R, are going to be correlated. So what that means is when you go to explain variance, like you put in x1, you'll find that x2 and x3 all share a lot of variance. They're all related. And so once you put that one in, you'll find you'll knock out other variables. Each of these individually would correlate quite well with y. When you do correlations, when you chuck them all into the same equation together, they gobble up each other's variance. So a good example is if you put in, for example, general health, or Kessler 10, psych distress, put in self-esteem, satisfaction with life, all three will be highly correlated with one another. Individually, all correlated with some other variable, which might be, how well you're doing at work or something like that. But because they gobble up each other's variance, whichever one gets in first will stay and the next ones won't get in. That's called multicollinearity. So it's a major bane of multiple regression. You get different results depending upon which ones you put in which order. And so often it makes more sense to say, well, you have some sort of hybrid measure that captures all three, or you just choose one of them and use that one as the best representation of psychological well-being as your predictor or something like that. It's a common problem you face. Okay, well, there are three types of regression. The most basic one is what's called standard regression. This is where you've essentially got the y variable, and you just put in a series of variables to predict it. So standard regression is just is where you've got you might be faced with a software where you've got the dependent measure, and you just put in all the variables together. So you might have age, self-esteem, stress, whatever else. You just put them all in together. Big happy party, in they go, boom. And that's called standard regression. You're not putting them in any sort of special order. You're not sort of saying, oh, that one's more important than that one, needs to come before that one. Just putting them straight in. It's a bit like gobbling a pizza. So you've got sort of, there's the variance. You're just going like this. In go the variables. And then you look and see, well, only 3 of them come significant, so I'll chuck out those other 2, and then rerun it just for the significant ones. You come up with a model then that's got the ones which make sense, which are significant. That's standard regression. The next type is what's called hierarchical regression. This is where you... anyone know what that one's all about? What's hierarchical regression?
There are the variables that can predict the outcome, but we put them from the most significant to
That's
which one is the most important? Which one?
Yeah, to get close, yeah, that can almost be the stepwise or the statistical one, yeah. Basically, the idea with hierarchical is that you've got some sort of underlying theory that says, right, this variable should go through first, should be modelled first before some others. So a common thing in many studies is that people have variables which have what's called logical primacy. Logical primacy means that the variables probably come first. You control for those things before you start controlling for other things. So, for example, most common things you often put through on step 1, which are logically come first, are things like age and gender, or a person's sort of socioeconomic background or something like that. So you control for those sorts of variables often on the first step or the first model. You say, right, I want to look at these various psychological predictors, but I need to control for age and gender first, because I know that gender does relate to these variables, the predictive, or the outcome variable. And so you put those variables first through on a model on step 1, and then you might say, right, step 2, I want to look at how much psychological variables contribute, or social variables. So I put those through as a group. On SPSS, you just click next, off they go through. In model 3, I'm going to look at psychological variables having control for demographics and the other social variables. So you're putting your variables through in a systematic, theoretically driven order based upon your actual theory. And that's what we call a hierarchical model. So you're putting things through based upon what you think should come first, either because those things logically do come first, or you want to separate out the amount of variance that particular types of variables explain. So that's hierarchical regression. That's often seen as a more robust form of analysis because it's based upon what you're controlling the model, deciding what goes in which order. And then the final version is what's called statistical or stepwise regression. It's called statistical as well, stepwise. That's where essentially the statistical package determines which variable explains most variance and puts them in the order of the highest correlation. And there are several types of stepwise or statistical regression. So how this works essentially is like this. You've got you've got your y variable, and you've got a number, you've done a correlation matrix, and you've got about 5 or 6 variables all correlate with your y variable. What the software does in the forwards method is to say, right, the first variable which goes into your equation is x1, which has got the highest correlation with y. So it bases upon statistical criteria, or criterion. So the highest correlation, boom, that one goes in first. And then it looks down through all the other variables and says, right, which of the next variables is going to explain the next most amount of variance? In fact, what it looks at is the one that's got the highest partial correlation. I'll explain what that means in a minute. And it goes, right, x2, you're in. You've got the highest partial correlation. And it goes to x2, finds another variable, right, x4, you're in, you're the next biggest one. And it keeps on going until the variable it adds doesn't explain much additional variance. The model reaches what's called a tolerance point. So most of these models have, and the software have what's called tolerance. So if you're adding in, the tolerance is often like 1%. So if adding in a variable only explains like a micro level of variance, like this one here, you know, a little tiny bit of extra variance, like is that little bit there. This variable here might be considered, it reaches the tolerance limit. Basically, the software says, no, you're not explaining anything useful by adding that additional variable in. It only explains less than 1% of the variance. It meets tolerance. It doesn't reach the tolerance limits, it's out. And so the software will say variables in the equation, variables not in the equation quite often. And the ones not in the equation are the ones that haven't explained enough variance to get to join the party. The bit of pizza they've nibbled off is so small, it's not enough to count. So it's out. So, now, there's different ways you can do this. There's what's called backwards. The backwards form of regression essentially involves throwing all the variables in, it's a bit like pick-up sticks. You throw them all in together, so that the pizza is all gobbled by all these variables, and then you start taking them out smallest ones at a time. So you take the first one out, does it reach tolerance? Yes, it does. It only explains about 0.5% of variance. Take the next one out, R squared hardly changes. Then, taking that one out, R squared drops 2%. It's too much. That variable is important enough to stay, and so it stays there. So the backwards way simply means you put them all in first, then start taking them out until it starts to make a difference. And when it makes a difference, you keep the variables. All the rest probably explain enough to keep them. And just to be really confusing, SPSS has an algorithm called stepwise, which is a stepwise method. Just to be confusing, these are all stepwise methods. The stepwise package basically combines the forwards and backwards method. It essentially puts the variable in the highest correlation, and then the next one with the highest partial. Then it goes back and checks the first one. Are you still gobbling enough pizza? Yep, okay, you stay in. And it adds number 3, you're in, okay, it's going to check 2 and 1 again. Yep, okay, variable 2. The other variables have hogged most of your pizza, so you're not really taking much of a nibble anymore, you're out. So it does it that way. And so, also there's what's called adjusted R squared, I'll just mention. That's where, when you chuck in heaps and heaps of variables, like 100 variables in, you could probably nibble lots of pizza away like a bunch of mice. You know, you could have like 100 variables, each of which nibbles away at the pizza and explains a great big amount of variance. But in fact, each individual variable explains nothing much at all. And so what adjusted R squared does is it adjusts your R squared down based upon the number of particulars you've included. And so it effectively corrects for you what's called almost overfitting the model, over-explaining the model. You see dodgy models out there where you look down and explain 30% of the variance, and they've got like about 50 variables or 40, all of which there's nothing in any of them. And so adjusted R squared would actually correct for that and say, well, in fact, you haven't explained very much variance at all, really, when you correct for the efficiency of what you've done. Let's check I said, okay. Now, the reason why statistical regression is considered a little bit dodgy is that it's influenced by type 1 errors. So if you've done a particular, you'll be familiar with the fact when you do a correlation in any study, it might just be significant by chance. It could just be by chance you've got a significant result. If that's the case, that's entirely going to drive which variables are predicted to go into your equation. because the statistical regression bases the entry of the variables in regression entirely upon the correlation magnitude. And so if your correlation is dodgy, it's by chance, it's a type 1 error, then you're going to be stuck with a model that's going to be dictated by chance. And so when you do another sample, another study, which by chance gets a different correlation, your model may be different. So there's always a danger that using statistical regression you get what's called model inconsistency or unreliability, because you're subjecting your statistics to the vagaries of chance. Whereas when you use hierarchical regression, you're basically upon theory. Each time you're doing it the same way. And it lives or dies based upon what you say it's going to do. It's not based upon the vagaries of what statistical effects might have emerged in a particular sample. Now, I'll explain the difference between partial and part correlations. Once again, I've done my board notes, put them up in that PDF so that when you watch back over this or if you're listening at home, you can have a look. I'll see how we go with doing that again on the PDF, otherwise I'll do it on the board. So the basic logic, you guys at the back see it okay? That's okay to see, yep. Yeah, the basic idea is that when you run your first variable, so this is once again y, this is the amount of variance that you're trying to explain, you run x1 and it takes a chunk out of the pizza. It explains that amount of variance. All this bit that remains here is not explained. So when we add in x2, second variable, what you can now see, the unexplained variance, this bit here, is given by b plus d. So the previously unexplained variance is b plus d, that amount there. See, that's the unexplained bit until x2 came along. So the partial correlation is defined as the amount of previously unexplained variance that x2 picks up. And you can see the amount which x2 has picked up is C. It's D. C is the bit which they both share. x1 and x2 both share C, so that's the shared variance between those two. So D is the new bit in Y which x2 explains. And so D divided by B plus D, so B plus D being the unexplained variance, D is the amount of explained variance which x2 has contributed. So the amount of previously unexplained variance picked up by x2 is what we refer to as a partial correlation. It's the new bit of pizza which x2 has gobbled on its own. And that's how the software basically works out which variable to put in next. It adds the next variable, which one gobbles the most previously ungobbled pizza, basically. There's also another concept, what's referred to as a semi-partial or part correlation. A bit statistic, talking about pizza at lunchtime. Yeah. You might ask, how much variance does x2 or x1 explain uniquely? And so the amount of unique variance explained by an individual variable is referred to as a semi-partial or part correlation. I'll also write it out. So it's given the name of the part correlation in some software packages or the semi-partial. That being my attempt at an M. Yeah. Part or semi-partial correlation represents that little bit there divided by the whole lot. So D is the unique amount explained by x2 that's not accounted for by x1. So D divided by A plus B plus C plus D, which of course is the whole of Y, is the value of the semi-partial or part correlation. So if someone ever sort of asks that question, how much variance does one of my variables explain uniquely on its own, not overlapping with any other one, just on its own, that's the semi-partial or part correlation. And that's given by, D over A plus B plus C plus D, the whole lot of Y. That makes some sense. Yeah, it's a unique bit of pizza which is nibbled. So that's the difference between those two concepts. Okay, partial correlation is the amount previously unexplained and now you add x2, and now you've picked up d. You've explained d. So d over d plus b, which is the previously unexplained bit, gives you the partial. Yep. Semi-partial is d divided by the whole lot. The unique amount of explained by x2. Okay. Let's have a look. Go back to the PowerPoint. There we are. All right, let's move on to mediation versus moderation. Anyone think they might be doing a mediation or moderation in the thesis this year? Might be one, at least one? Yep. Okay, mediation essentially means the relationship between A to C is carried by B. So for example, let's say A is workload, and that's job satisfaction. So you've got, essentially, job satisfaction is only affected negatively when people get stressed as a result of their workload. Some people are doing work they really love doing. There's many aspects of this job, writing papers, doing some teaching, you do some stuff. You can do lots of it, and you sit there in the inbox and you do it, and it doesn't make you feel bad. It only gets bad when it causes stress. And you've got stress coming in. That usually means lots of inbound questions about stuff that's going wrong, or the university is demanding this, that, and the other, or something's not going right. That causes stress, and that's when your work satisfaction drops. So the basic idea is that A is only related to C because A leads to B. So B carries the relationship to C, if that sort of makes sense. So you might be in a job, you might be an artist or someone, painting all the time, but you love it. You can work as many hours as you like and you're still quite happy about it. But when your workload leads to stress, too many things happening at once, then that could lead to bad work satisfaction. When can mediation be conducted? Now, to do mediation, all three variables usually have to be correlated significantly. However, I'd add to that the proviso that it's usually better when all three are correlated in a similar magnitude. Let's say it's like 0.3, 0.4, 0.5, something like that, and if they're in the same direction, all positive or all negative. When there's a mixture of positive and negative, like A to B is positive and B to C is negative, you can get weird effects occurring in mediation. It works better when they're a similar magnitude in size and they're all in the same direction. Because if they're not, you can get weird things called suppression effects. And tomorrow's assignment has been written, all the data I use is dodgy, made up stuff which has a nasty suppression effect. You basically run the model and the effect reverses the direction. The variable which is most notorious for doing that is gender, because people often think you can get different effects for men and women, and then when you run and control for gender, suddenly you realise, the effect you're getting overall is not the same across the two, and then suddenly you're getting weird effects. Now, the most common way in which you see mediation tested is use what's called the Barron and Kenny method. Although it has to be used with caution, it usually works best when you've got, as I said, the correlations in the same direction and a similar magnitude. If they are, you can usually safely use this method. You do it like this. Essentially, so you've got A, B and C. What you do is that B is, of course, the mediator. So A is your predictor, C is your dependent measure, B is the one in the middle, that's the mediator variable. So really what you're trying to do is how much is B mediating the relationship between A and C, the ones on either end. So what you do, you try to work out how much does the predictive power of A, predicting C, go down when you put B into the equation as well. So we know that A predicts C, do a regression with A predicting C, it'll be significant. It'll be the same as a correlation. what happens if you put B into the equation as well? Does it kill the relationship between A and C? Does it change it? And this is what's called, you're looking for evidence of partial versus full mediation. So I'll come back to that in a minute. So essentially, I'll go now to the handout. I could make the same sort of example. Yeah, the basic idea is the way in which you do this. Let's check. I think I do have. Let's have a look. Sorry, let's go back to that again. Yeah. So here, the way in which you run it is that the first model you run is A predicting C. So you just run a regression with A predicting C, a single predictor, and then you run it again with B in the equation as well, A and B predicting C. So A is there and you put B in separately on top of it. What will happen is the A coefficient will change because B is explaining some variance. And what we look for is changes in the coefficient value of A predicting C. Now, in the first equation you can see, let's say A is predicting C 0.56. That's a pretty strong relationship. It's getting up to what's quite strong. Then you put in B, and you can see it's dropped to 0.41. That would usually be described as partial mediation because you can see A is still, still reasonable magnitude. It's still related to C. If, on the other hand, you go from 0.56 and it becomes not significant, or in fact if it reverses, it actually goes the other direction, we'd usually describe that as full mediation. So where introducing the mediated variable in the second equation leads to the effect, or the original effect dropping and becoming not significant or virtually nothing, we would call it full mediation. And we also, if we've got a suppression effect where the result actually reversed to like a negative, which it does tomorrow, we'd also refer to that as full mediation. So adding in that additional variable, the mediator, is strongly mediating the effect. It's changing the relationship between A and C. Yeah, that's a suppression effect. Yeah, possibly. Yeah, it's rare, but it would usually drop it. Yeah, I haven't seen one that's where it's gone up, but not mathematically impossible. Yeah. Okay, now this is the Barron and Kenny method. Now, if you guys are in fact doing it for your thesis, the recommended method, if in fact the correlations are a bit different in different directions, you're better off using the bootstrapping method recommended by Preacher and Hayes. I'm not going to go through and teach that because so few of you are probably going to be using it. But I've given them in the handout a full guide to how you download the macro and store it in SPSS, how it all works, and so all the information you'll need to use the Preacher and Hayes method is in this handout. So you can use that if you need to use it for your own thesis work. It won't be something I'll be asking about in the exam or anything like that. But it's just there for your reference. Okay, let's have a look at the other one. That's moderation. Let's go back to, here we are. Okay, moderation effect is where essentially, it's a bit like an interaction in ANOVA, if you're familiar with interactions. The basic idea is that there's a relationship between A and C, but it changes depending upon the level of B. And so once again, you could use stress as the example, as a moderator of workload. Just say, for example, workload leads to job satisfaction. It may well be high work hours and low job stress. You're an artist or someone doing something you really love doing. It's an enjoyable part of the job. You actually have a good job satisfaction. You're quite happy to do lots of work because you like the work. If, on the other hand, high work hours leads to job stress, so it's 50 people chasing you rather than 5, or difficult customers or difficult something or other, then that leads to lower job satisfaction. So high work hours combined with low stress job, satisfaction is good. But high work hours combined with stressful parts of your job, then lower job satisfaction. And most people realise that most jobs, it's dealing with complex people, and that sort of stuff is often the most difficult part of sort of many jobs. So the effect is moderated. In other words, the B acts as a moderator of the relationship between A and C. In effect, there are different relationships between A and C depending upon the levels of B you're looking at. In mediation, you're really just talking about one effect, A versus C, and how that changes with the mediator. So how do you conduct moderation analysis? It's a little bit more complicated than doing, we're doing one tomorrow. By the end of tomorrow, you'll be able to do a moderation. Now, many people talk about centering the variables, but you don't really have to do it. I've sort of done it, and it doesn't make a lot of difference. Basic idea is you just multiply A and B together. So in your data set, you'll have your dependent measure you're trying to predict, that your C variable. You'll have A and B, your two predictors. What you do is you just multiply A and B together to create a product term. So in SPSS, you go into compute, you go into data, compute, and you might call it, I think we call it gen age tomorrow, gender times age. Gen age, and the box you write, it's gender star times age. OK, creates a new variable called gen age, which is just gender times age. So you get a product term, and you conduct a hierarchical regression. You put the two main effects, or A and B, on their own together through on the first step, and then you test to see if your interaction term, which is you've just calculated, A times B, is significant on step 2. If it is significant, then you've got yourself a moderation effect, interaction. That's what you're often testing for. And of course, you can do this for three-way interactions as well. In some of the occupational health research, what's it called, the demand control support model of work stress. You might have demand times stress, demand times support, support times demand, and you might have demand times support times control as a three-way, and you do that one right at the end after you've just done the two ways. So hierarchical regression can be used to test for two ways as well as three ways. But we'll stick with a simple one for the time being. So your interaction comes up significant. Right, the question is, how do we actually explain why it's significant? What's the interpretation of the interaction? And that's the tricky bit. So you see it's significant. If not, there's no moderation. Okay, what's the nature of the interaction? Well, what you have to do, what effectively this interaction means, or the moderation means, is that the relationship with A and C differs depending upon the level of B. Now, if your second variable, your B variable, is gender, it's easy, because you say, right, it means that the relationship between A and C is not the same for males and females. And so I've already got males and females in a, men and women in a column. I can just select cases equal male, run my A versus C for males, and go in, select women, run it again, and I'll get two different equations for men and women. And if I plot the actual lines, they should be like this. They'll be different. They won't be parallel. They'll differ in slope. That's why I've got myself an interaction. If, on the other hand, your second variable is metric, it's not binary, then what you've got to do is create a binary variable. So what you do is, say your second variable is something like stress level. What you do is you just go into your package and go, right, give me the median for that variable. You know, SPSS, you go in and you ask for descriptives or frequencies and ask for the median. Right, got my median, write it down. Okay, compute or recode. Anyone who's the median and above, okay, you're group 2. Anyone who's the median and below, you're group 1. Right, select group data group equals 1. Oh, little filter comes on. Right, regression for A predicting C for group 1. Right, now select group 2, do the same thing again, there's your two equations. So you do it that way. So once again, tomorrow I think it's gender, so you don't have to worry about doing this, but that's how you do it in practice. If your second variable is a metric variable, you have to use a median and do a recode or compute to get your two groups. So moderation. Essentially, you just you select group 1, A predicting C, group 2, A predicting C. You take the two equations, so you get two separate equations, as you'll see tomorrow in the lab. There's slightly different slopes, slightly different constants. What you then do, an example we're looking at tomorrow is age predicting memory functioning for men and women. And you can see this will be a significant moderation because you can see that the relationship is not the same. The lines aren't parallel. So in order to get a plot like this, so you'll have these two equations, age predicting memory functioning for men and women separately. You can sort of write them down from the output. To get a plot like this in Excel, you just put some dummy values of age into an Excel spreadsheet, just 20, 25, 30, whatever you want to put in, right up to say 80. If you want to capture a Jedi, you might go up to 700 or something, I don't know, or Keith Richards, but up to 80 or 90, and then you put in equals you put in as the function command, you put in equals the equation times the first reference age, then a little black dot, you can just drag it down so it then does the predicted value for all the ages in your Excel. You'll see how this works tomorrow. Select it all, do a plot, and you've got your a plot like this. So how many people are familiar with using Excel and functions in Excel? Have you used that much? Yeah. It's useful to know. So it's very useful for doing things like calculating your mortgage and things like that. So you put in functions and you can just calculate functions based upon set data that's in the spreadsheet. I use it to calculate my solar savings. I've got a solar array on the roof. You can sort of put in the figures and plug in the figures off the meter, and then it tells you how much you're saving. It's very, very handy skill to have Excel. So we'll be doing all that tomorrow. Last thing I'll talk about before we have a break is just some of the assumptions of multiple regression. I think, did you cover some of these with Rachel last year? Talk about some of the basic. So when you're doing your thesis, they often want you to say whether your linear regression was valid and robust. Often the word robust is the correct word to use in relation to these assumptions. This essentially refers to the distribution of residuals around the regression line. So let's have a look. So essentially, we talked about how you've got the actual values which don't quite sit on the line. Those bits there are called residuals, of course. Some of them are below, like that. What the software does is basically, in a good solution, a valid linear regression, it should look like that. It should be pretty evenly distributed across the whole length of the line for all values of age or your predictor. When they're not even, then you start to worry. And so essentially what it does, it turns it on its side and gives you a plot that looks a bit like this. So this is your basic regression line, and it plots the residuals around it, often standardising them using z-scores. And what you're looking for is something like that. You want it to look like that, even. Now, but nasty things can happen. This is why you look at when we talk about inspecting the residual plots, we look for violations of the assumptions. The first one is heteroscedasticity, which means something nasty like this, where you've got, the most common one is fanning. The residuals get really huge as you go up to high values of x. So as you're going up to the higher scores here, the residuals are getting bigger and bigger. They're not even across the line. What that means is your equation's not equally efficient or robust for the full range of your predictor score. That means it's getting a bit dodgy at the higher end, which may lead you to think about transforming your data. This could happen, for example, if I was predicting someone's expenditure on gambling. And you've got some people spending thousands and some spending a small amount. The equation's pretty good at predicting everyday behaviour, but as soon as you get to the extremes, it's becoming unreliable. So heteroscedasticity is a problem, which may be solved by transformation. Normality violations look like this. Is where you've got all the dots below the line, and only a few above. That means they're all sort of skewed in one direction. So it might be you've got a few high scores here, and then all the rest are sort of down here, and then the equation's still predicting right through the middle. So it's not. It might be that the plot looks a bit like you've got a whole lot of sort of weird outliers up here or something like that, and then all the rest of them down here, and those outliers are pulling the line that way, but all the main swarm of points is down here still. And so the line is, you've got non-normality, you've got a great big skew going that direction in your y variable. Other particularly bad one is non-linearity. If it looks like your line is in a straight line, and that means you're probably not using the right form of regression. So if it looks like, if for example you're getting something a bit like this, that means your points are probably quadratic. So you probably should be using a quadratic x squared type function for your regression rather than using a standard x function. You haven't chosen the right functional form for your regression. Or if you get like a sort of Loch Ness monster type thing happening, sort of like that, it could be it could be a sort of cubic, x cubed, type function that you need to put in. What's the other one? Non-serial area dependence is more sort of issue of time. If you're doing any sort of time, you won't have any trouble with this in a lot of psych research, but in a lot of economics research, what you tend to get is what's called autoregressive effects, where essentially all the scores will tend to sit up here, and then all sort of go down here, and then go sort of up. So scores here will tend to sort of correlate with the ones which came, here. So because there tends to be a sort of a serial effect. So for example, if you think of what happens in the world, there are certain things which become very topical, very meaningful for a certain period. And so scores on a particular scale or response scale might become very much influenced by what's been happening recently. And so that's referred to as an autoregressive effect. It won't be sort of like random. It'll be influenced by what came before, that sort of thing. Like, for example, attitudes to gun control in New Zealand at the moment, a sort of sad example. It would be greatly different now from what it was a week ago. And it may be different next year too because of the events of the recent week. That sort of thing. So, one more about path analysis. All right, I think we've reached your coffee break, and we'll sort of pop back about 20 minutes and talk about mixed models. Yeah. Step 1 is the same as statistical regression. That's where you're putting the variables in based upon...
So what is the same as what?
Statistical regression.
Okay.
Which means you're putting in the one with the highest correlation first, and the next variable goes in is the one with the partial correlation.
Okay. So this one is the same as this one, right?
These are all examples of that.
Okay. Yeah. Actually, forwards and backwards, they can reverse.
That's right, yeah. That's right. Forwards means putting them in one at a time.
Yeah.
In fact, you put them all at once and you pull them out and see if it makes a difference. Yeah.
Okay. And also, this one here. I don't know why this one could be higher powers. Can I say like lower powers as a?
You could, yes, you could.
It could also be like one time.
Yes, it could be low work hours makes you very bored. Low work hours times stress. So you've got a public service job where you're boring, you've got horrible people working and you're stressful. That can make you bad. So you could actually have an effect for that as well.
Okay. I don't know what is it.
Yes, yeah. Full mediation means that's what it was the first when you ran A predicting C. The coefficient for regression coefficient for A was 0.56.
And the other place is like A predicts C plus B predicts C.
That's right.
What's similar?
Yeah. So what's happening here is when you put B in, A is dropped to that. So it's gone from 0.56 down to nothing. So,
Okay.
yeah. So effectively A has been wiped out.
Okay.
And so that means that full mediation, B is, B effectively is blocking and explaining all the relationship.
Okay. And here is like when you make two credits say, right? This 0.56 and this one's also the same.
Yeah, but both same meaning alike.
Okay, and this one is room would include B.
Yeah, B's in there as well. Yep.
So and total and product like 0.41.
Yep, it's gone
And
down.
this one is like way like
It's gone way down. This one's only gone down by 0.15. It's gone down a little bit. This one's gone down totally. Yeah.
okay, nothing.
Yeah.
So
So the full mediation. Yeah. Full mediation is where it's the whole relationship disappears or goes really low. So here, this would still be significant. But that one, yeah, that's gone. It's total mediation. Yeah.
okay, what's the difference between partial and mediation?
Full mediation usually means the relationship doesn't exist anymore when B is included.
Okay. And the partial mediation is like A plus B.
It's A, including B as well, and A has gone down. A has gone down significantly, but A is still significant usually. Yeah. That's all right. Yeah. Yeah, that'd be great. I'll go through text and
Assuming there'll be something related to this.
that's no problem. That's all right. That's all right. But All right, guys. Well, I'll get back into it, and we'll take a look at mixed models. All right. So this is a fairly tricky area of statistics, but main thing to take away today is just some of the concepts and get a sense of why we do mixed models, and then tomorrow in the lab session you should get much more of a sense of how these things are actually done, and then when you sort of read back over the notes, do the exam revision, and then put it all together, you'll start to sort of make sense why you do this type of model. I must admit, it took me a little while to get my head around doing these models a number of years ago. I think it was about 29 or 10, I think I first realised I better start learning how to do these models, and then I actually read the books which had all the sort of equations on it, and that sort of made sense, and then I didn't actually know how to run the things in SPSS or any package, so that the challenge was actually sort of getting it to work. So I'll talk about the rationale for doing mixed modelling, and one of the things I'll be highlighting is the problems of aggregate analysis. This particular type of modelling is essential if you're looking at studies involving schools or big data sets where you're looking at where you've got different sampling units. So like you're sampling across schools or across different states or different hospitals or anything like that. A number of you go on to do research jobs working big data sets. You're bound to have this type of issue of there being different sort of groupings in your data. We'll talk about the difference between random versus fixed effects, what that means, the term which you'll see mentioned in the literature, some of the papers you're reading. If anything else, this will be useful to teach you how to interpret papers which use this particular style of modelling, because you may well not want to do it yourself or have the sort of data which is amenable to it, but you'll get papers where you have to interpret these types of outputs here. Okay, I will talk about the concept of levels in mixed models as well. And I'll just make a bit of a brief discussion about the difference between cross-sectional versus repeated measures analyses involving mixed models and why we have the difference. And this has various data formatting issues. We'll talk about variance components once again in mixed models. And a little bit about how we actually go about running and interpreting the outputs from these sorts of models. So a lot of this will become much clearer when you actually do it tomorrow. As I said, the main thing now is just to get you a sense of, that's what this is all about. Okay, well, we use mixed models because there are limitations with many of the conventional analyses which we use in psychology to analyse certain data sets. We don't really have a consideration of the subgroupings in the data, which when we're doing the... yes, you haven't got the PowerPoints here, you need to bring them up on my uni. Yes, I always used to print off lots of these things, and I was being told off, you're not meant to, but it's always hard to remember to print everything off. One of the issues is non-independent data. When you're sampling data from different subunits, the data is not actually independent like it should be as based upon the sort of models you should be using. We'll talk about some of these sorts of issues. The other issue is that these sorts of models are quite versatile. They enable you to run ANOVAs and also regressions in the same type of model. Now, to explain, it'll all start to become clear when I'll give you an example. Why do we use mixed models? Well, the main issue is that data in many research situations is not independent. An example I give in the notes on page 2 of the handouts is that, say for example, you wanted to look at the relationship between socioeconomic status and academic performance in high school students or secondary students. And you said, right, I'm going to go out there, I'm going to sample 2,000 secondary school students in South Australia, and I'll have SES on the x-axis, then I'll have academic performance, like might be year 12 scores or something like that, stage 2, whatever it is, on the y-axis, and you have a correlation between the two, and you say, right, I told you so, SES, high SES students get higher grades, therefore it's all about wealth redistribution, and therefore it's all about wealth leading to better marks. Problem is, what if it's also the case that wealthy students go to schools which have higher standards of teaching or other resources? It still means there's something to do with SES, but it may well be that what if it's the case that there's a whole lot of schools out there which have really good teachers, they're very highly paid, they're very good teaching. That could be the reason why the high SES students are doing better. It might not actually be related that as much to the SES as you think. I went to school with a number of guys whose fathers were multi-millionaires, and they were the bottom of the class. Yeah, they were not necessarily bright. And so what you really need to do is be able to say, well, let's hold the school constant. There's some schools out there which are a bit like that, where you've got students from a lot of different backgrounds going to the same school. Some of the high schools which are sort of straddling different sort of socioeconomic areas, where you might get students from wealthier backgrounds, those from not. There the teaching will be held constant. You've got pretty much the same school. Then you might well look to see if SES makes a difference within that type of school, holding the teaching in the school constant. And that will be a stronger argument. Therefore, you could wipe out the potential confounding influence of different levels of teaching standards or bullying policies that might exist in the school or something like that. So mixed models grapples with the idea that in many research situations you're faced with what's called a fallacy of composition. That is, you say, based upon your 2,000 students, that SES is related to better performance, but you might find when you go to one school, yes, there's a positive relationship. You go to another school, yes, even better. Then you go to another school, it might be negative. It might be kids who are really wealthy, they're the sort of frat kids, they're going to work around, they're going to drink all the way through college. The Trump family type effect, the wealthy knobs from England, sort of the old sort of thing, hello there, don't really study. Brideshead Revisited type sort of thing, Another school, it could be no relationship at all. And so different schools could have completely different relationships. So it may well be, for example, in a school where everyone's really wealthy and all the parents are pretty smart, and that's why they've earned high incomes and they've sent the kids to the wealthy schools, you get virtually no effect. The SES range is really narrow. A lot of the kids are bright, and maybe 80% of them are all pretty able, so you get virtually no relationship at all. It might be another school where you have a lot of diversity of backgrounds. Some students, come from backgrounds they've never studied at uni before, first generation at uni, not a strong academic background. Other kids who come from an area with a strong educational background, both parents professional jobs, might be a really strong relationship. And so when you just do this overall analysis, you don't capture the fact that you've got all this variability within the sampling units, different schools which you've used. And so basically you can actually see the y-intercept may vary quite substantially across the different schools. It's subject to its own distribution. And the slope parameter, 0 here, pretty strong here, pretty good here, but not in other schools. And so there is a problem that you're not capturing that level of variability in your study. What effectively is happening is that the data from one school is not strictly independent. So if you sample 400 or say 200 cases from a wealthy independent school, all those kids are going to be very similar to one another. Academically, possibly because of the common background they come from, the common type of school. Or if you're studying bullying, for example, it may be you've got one really rough school with no bullying policy. Some kids are really bullied, some aren't. We've got another school that's very strict about bullying, has a very strict policy. There's no bullying going on. And so it's virtually flat. There's no relationship at all. So you can sort of see the type of problems. You can imagine you can extend this to the workplace. You may have places where everyone is stressed. Think of Flinders recently with a big restructure. People just walking into a room and going, right, go back to your computer and open up a document and your job's gone. That's what they did. It happened with our professional staff a few years ago. And it's very stressful. So the whole place will have a certain level of stress because of this sort of common event. So this is the reason why mixed models is a way of trying to capture the fact that you've got non-independent data in your data set, and also tries to capture and model that sort of variability of your overall effects within the subunits in your data set. I'll sort of explain that in a bit more detail. Now, in mixed models, we encounter the difference between what are called fixed versus random effects. Now, a fixed effect is just what you're familiar with. It's a standard just variable which predicts something else. So gender, age, any sort of variable which you measure, you put into an equation, an ANOVA or regression. You've been dealing with fixed effects every time you've been doing that. It's just a standard variable or independent variable. Random effects, this effectively has two meanings. The first meaning is that when you sample things like schools, so you go out and get 2,000 young people and you measure, you record which school they come from, it's very likely you're only sampling some of the schools. There's a whole lot of other schools you didn't get. And so, in effect, you've only sampled a subset of the potential range of schools which are out there. And so, whereas with gender, you've captured usually all the dimensions. You've just got age that's captured fully, IQ is captured. With schools, that's referred to as a random variable because you haven't sampled all the potential units of school which are out there. The second reason why we call it a random effect is that we can model variations in the relationship between X and Y across the different sampling units. In other words, we can, for example, if we've got this variable here, which might be SES, predicting academic performance, we can model that as a random effect and say, right, I'm going to model this as a random effect, and I want the model to see whether, in fact, there are differences in the y-intercept across the different functions in the different schools, and to test whether the slopes are different as well. So you actually, when you model a variable as a random effect, you're effectively modelling it across the levels of the random variable. Is the relationship the same or different depending upon the which school it comes from? And so when you're doing SPSS or using a package, you'll have one variable which tells the package my data is nested within schools. My data and of course you can use a combination variable that tells the package, okay, my data is nested in schools. SPSS is called a combination variable. You actually say combination variable and you'll be saying school. Or the example tomorrow I think is hamburger joints. You'll be saying hamburger joint or which one it is. Mixed models is a form of what's called hierarchical linear modelling. Different terms are used, but hierarchical linear modelling, HLM, you hear that term used, HLM, or it's often referred to as multi-level model, MLM, is also used. So HLM, higher linear model, or multiple linear model, or mixed models means this type of design. Not to be confused with mixed methods, which involves, like Deb's research, qual and quant together, just something different. Or mixed ANOVA, which involves repeated and between factors. But basically, this type of model introduces the concept of levels. Data is nested. So an individual student from a school comes from a particular class. That class is nested then within a year level, and that year level is then nested within a school. Within the longitudinal study of children, the LSAC study, they have weights which capture the fact that households are sampled within local government areas. Multiple children are sampled within families. So there's multiple sort of nesting factors involved with that study as well. So if you do a study at the university, for example, there'll be people like me I'm in the School of Psychology, which is nested within health sciences. You're doing a study of nurses, they'll be nested within critical care nursing or neonatal nursing or something like that. There'll be different groups. This is what we refer to as nested data. Any reading papers we've seen the term nested data used? This is what it means. It means things are nested within something else. And people will be nested in a way because they're similar in some way because their particular teacher is a particularly good one or a bad one. We know from school you have certain years where you get a great maths teacher or physics teacher, another year you get a really bad one. And that makes a big difference to how you perform. And so all the students in year 11, for example, I had one teacher who didn't teach a third of the textbook. And we got the exam and we hadn't been taught 1/3 of the textbook. So our whole class was effectively nested in a situation where we're all not going to do that well because we didn't know, we just sort of guessed a lot of the answers. We hadn't done the whole section of it. The guy sort of said, "Oh, sorry guys," afterwards. We're too sweet. Yeah. So the cross-sectional version of mixed models is where essentially you're testing for hierarchical structures like this. how much of the variance between in a model is explained by individual differences between people versus variance they share as a result of coming from the same school or the same class. That's what the sort of questions we're asking. And we're also, of course, asking how do the functional relationships vary across the groups. So a cross-sectional, so if you're doing a school study, you should be doing mixed models for your study. You try and publish it without doing it, and you'll get your paper rejected, because people will say, well, how have you dealt with the hierarchical structure of the data? It can be done in the repeated measures form as well, so we won't be doing this particular method. What's happening there in repeated measures is that you've got, because some of you will go on and probably do jobs where you get faced, so say you've got time 1, time 2, time 3, you've got a whole group of individuals like this. You're going to be measuring, getting data from these people, the same people across time. So observations from each person, each time is nested within the participants. See, so repeated observations are nested within each individual. So the lowest level of data is the observations, the next level up is the individual. So you can see how it can get very complicated. In a school study that's a longitudinal study, you could have data, observations which are nested within the individual students, who are then nested within classrooms, who are then nested within year levels, and then nested within schools, which might then be nested within LGAs, and it could get very quite hideous. But basically, you can partition variance around those different levels. Now, the reason why we do mixed models for this type of design quite often is because there are problems with the covariance assumptions. Standard repeated measures assumes that time 3 and time 2 will be equally correlated as time 3 and time 1. But imagine if this were a study of a person who was depressed, depression. You're much more likely to be depressed at time 2 if you're depressed at time 1 than year 3 when you're in time 3, because 2 years have gone by, you probably got happier. And so when you make the assumption that things closer together probably are more likely to be correlated than things which are further apart. And so what these sort of models allow you to do is change the assumptions you make when you run the models. When things like that happen, for example, people are depressed in time 2 because they were probably depressed in time 1, we refer to that as an autoregressive effect. It's autocorrelation, because the two things are basically occurring pretty similar in time, and so you can actually specify different covariance structures which make assumptions about that type of thing. Not something to worry about, as I said, for this year, but that's the reason why you do it. Data issues. Cross-sectional analyses are easy to run. You just run them as you'll see tomorrow, just using a conventional data set, which tells you which subunit people belong to. Repeated measures use what's called long-form data. So if you encounter this in a job next year after honours, what you'll find is that, say it's a longitudinal study, each person will appear 3 times. So you'll see person 1 with their little ID, their gender will be 3 times, their age will be 3 times, so there'll be sort of invariant variables which appear in 3 waves. Then there'll be a variable saying 1, 2, 3, wave 1, 2, 3. And then their different scores across time. So for self-esteem, you'll see their score for time 1, time 2, time 3. Their scores will be changing. Other things will be invariant, say the same. So the data has to be changed to long form to run these types of models. Each measurement point has its own data line. So a study, for example, 1,000 people measured 3 times requires 3,000 data lines. It has to be, SBS can transpose the data for you. Yeah. Now, variance components. The important concept with mixed models we'll see tomorrow is that we're able to capture how much variance is simply between individuals versus the groups they belong to, or the school they belong to, and tomorrow we're looking at the McDodgy burger, hamburger joints. How much variance is associated with what burger joint you work at. And so what SBS will do, it'll have a thing called test for covariance parameters, and it'll have a little thing called, it spits out a residual. So I'll bring it up on the handout in a minute. You'll have a little thing like a residual. then it'll have sort of subject within school or hamburger joint. It'll have like a figure like this. It might be something like, and you add those two together, I think it's 0.70. So this bit here is the amount of variance. If you divide that, this is the total variance. 0.25 divided by 0.7 is the amount of variance explained by what school you belong to. And that's quite a large amount. That would be sort of about more than a third. And when you see that, and that value is referred to as the intra-class correlation, ICC, the intra-class correlation. And when that's quite big, and this is actually quite a big value, that tells you that you've got a lot of nesting and clustering happening. So when the ICC, the intra-class correlation, is quite big, that means that tells you probably should use a mixed model, because you've got a lot of variance shared by people's school, by the fact that they belong to the same school, or the same burger joints, or the same faculty, or something or other. And that strengthens your conviction that you should use this type of design. When you run mixed models, there are different types of variables. So you have a subject variable, which will tell you, what your combination is. So school, I think school is going to be one you'll encounter quite commonly. In mixed models, when you use SPSS, there are some variables which are going to be nominal variables, like gender, whether you smoke or not, things like that. They go in, those sort of binary variables go in as factors, a bit like a normal ANOVA. The metric or continuous variables get put in as covariates. So you'll see two little boxes. When you go to mixed models, it looks a bit like a combination of regression meets ANOVA. You have at the top dependent measure. Yeah, that's easy. Pop that one in. Then you'll see factors and then covariates. You put the metric variables into the covariates. You put the factors, binary ones, into the factors. And then you can then model variables as fixed factors versus random factors and so on. The combination variable is like the burger joint, or the clustering variable, the school, which you'll see. Now, I'm not sure I've got access of. So the first window, you'll see a subject variable, and then dependent measures, factors, and then you'll have all the ability to put in the fixed effects. This will all become clear tomorrow when you actually get SPS in front of you. Now, what I might do is see if SPS is on this. I don't think it is. It'd be nice if it were. I'll just type in. No, not here. Not useful. Yeah, never mind. I'll just be potluck if it did. It was there. It were there. So if we go into My Uni, I'll show you the stuff I've put up for running the lab tomorrow. You won't need that one anymore. Courses. Search methods. Okay, so go into here. Now, tomorrow you have two exercises to have a go at. There's going to be a multiple regression exercise. Might sort of show you that one first, and then we'll look at the mixed model one. Multiple regression one gets you to run a mediation followed by a moderation. This one here. And the data for this one is available in the Excel spreadsheet from last week. So you go on to about tab 3, you'll see memory, intelligence, age, gender. Just cut and paste, boom, into SPSS, you've got that one, that's all there. So what we're going to be doing is how well does gender and age predict memory scores. So we're going to be running a multiple regression with those two as predictors. And then does intelligence mediate the relationship between age and memory performance? So the first one here, and then do a moderation. So is there a significant interaction between age and gender and memory performance? So for the mediation, we just use the Barron-Kenny method. You'll be putting in memory performance as dependent. You put in age on the first step, and then the second step, you put in intelligence. You can run this as two separate runs. You can just sort of do the age one, look at the output, and then go back in and add intelligence and look at it. So you're looking to see whether the age coefficient varies. Once you put intelligence in, it should sort of drop. In fact, it reverses to a sort of suppression effect. Second one is a moderation, where you're going to be looking at the relationship between gender and age. So what you do is you're multiplying these two together. And then you're going to be putting in gender and age, predicting memory scores, followed by gender times age as an interaction. And then I've got instructions here on how you go about actually plotting this in Excel. So that's the first assignment tomorrow. So you'll be doing putting in the equation and using Excel to. It all makes sense when you start doing it tomorrow. Yeah. So by tomorrow you'll know how to use Excel functions, and you'll know how to plot and interpret a moderation. Mixed models. So we'll go back to the mixed model data has already been done for you. So it's in SPSS all there. You just open that up, click on that one, and you've got the data straight into SPSS. And then I've got the output with comments, and then I've got the actual exercise you'll be doing. This is this one here. So essentially you've got what factors contribute to staff turnover. You can see it down the back, and then make it a bit bigger. That's good. You've got so people work at 30 different McDodgy burgers. Each place has a different location and known to be slightly different in terms of sales, customers, and so on. Predictors of job turnover. We've got age, gender, then we've got smoking status, BMI, how stressed you are, job satisfaction, and of course there was an identifier indicating which store you come from. This is quite clearly a multi-level problem because people are nested within different stores. It might be you work in Heine Street getting people throwing things at you. Who knows? Yep. So how do you do a multi-level model? Well, tomorrow, as I said, it's what's called a model building procedure. It's basically what you do is you start by running what's called an intercept-only model, where you don't include any predictors. And the key thing you look at, there's what's called a indice of model fit called the log linear likelihood ratio, which is this value here. And essentially you add to the model to see if you can actually bring the value of that down. Now I'll explain on the output how you do that. And essentially then you're going to be adding in some fixed effects, just like normal regression or ANOVA. You're chucking in age, gender, and all the other predictors to see if that predicts job turnover. And then in the final stage, you'll be adding in a variable and modelling it as a random effect to see if, in fact, the effect varies across the different burger joints. And so the output's going to look a bit like this. When you first do an intercept-only or base model, which is like a sort of starting point with nothing in it, you essentially get the following results. You get a base log linear likelihood ratio of this, and then you actually see the residual variance shows that about 15% is shared between the burger joints. So it's not that high. You can always get away with not using mixed models, but it's still enough there to maybe be of interest. And that's the intra-class correlation component. Now it gets a bit more interesting when you get to the second model, where you actually put all your fixed effects in. And what you see is your value here has gone down. And of course, you can test whether that's a significant improvement on your model by using a chi-squared test. And that's based upon taking that from that to get the value of chi-squared. And then degrees of freedom are given by the number of parameters on model 2, which is 8, take the number that was in model 1, sorry. So 5. And in fact, that's such a huge value of chi-squared that your model is definitely showing an improvement. So adding the fixed effects has improved your model. So, and what you then do is you go to a fixed effects table to find out which variables are actually significant in your model. And I think you'll find that stress is significant, BMI is approaching significance, and so on. And the final model, then we're going to be running stress as a random effect to see if the model gets better again, and it does. It's all rigged data. So, and the final interesting thing we'll look at, SPSS produces this bit here, which is essentially, this one here tells you whether the intercept or the average value of job satisfaction varies across the stores. And that one tells you whether the slope parameter, expressing the relationship between stress and turnover and tension, and job satisfaction, is varying. And then this one here tells you if those two things are correlated, whether in stores where there's a high intercept, whether the job satisfaction is, the actual slope parameter is lower. But they'll make a bit more sense tomorrow. So essentially, it's all out there for you tomorrow. You just follow the instructions through, and I'll be coming around, of course, to make sure you get all correct. And I've got the output from the model as well. So you can sort of see this is definitely a multi-level problem where you're trying to predict job satisfaction using a variety of different predictors, and where you're able to take advantage of some of the multi-level components. But to have a read through that tonight before you start tomorrow, and then hopefully this will make a little bit more sense when you come back to it tomorrow. But I said it's not something if you don't get it right now, I wouldn't get it right now because I didn't. I had to read over this a number of times to get my head around it. It's not an easy area of modelling, but as long as you've got that sort of general sense of why we're doing these sort of models, the notion that we've got interdependent or related data where you've got these subgroupings, which makes the relationships different. All right, I'll leave it there. So I look forward to seeing you guys tomorrow. Yeah.